Hi, everybody. My name is Alexa Williams, and today I'm going to be going through a couple of learning objectives in Chapter 15, which is all about blood flow and the control of blood pressure. The first learning objective is learning objective 15.6.2, which talks about the velocity of blood flow in the capillaries. And we know that capillaries have a very extensive network with a large total cross-sectional area in the body. And so even though each individual capillary has a tiny diameter, the vast number of capillaries combined significantly increases the overall cross-sectional area. And because of this, capillaries exhibit a sort of splitting or division of blood flow into numerous small channels. And according to the principle of continuity, when the total cross-sectional area is larger, as seen in the graph on the right for capillaries, the velocity of blood flow decreases, as seen in the graph on the left for the capillaries. And this is a consequence of the same volume of blood having to pass through a much larger space, which results in a slower flow rate. And this low velocity in the capillaries is especially advantageous for their primary function, which is to facilitate the exchange of essential substances through tissues and the bloodstream. So, a slower flow rate allows more time for these molecules to diffuse across the thin capillary walls, which ensures the effective exchange of those substances. The second learning objective is 15.6.4, which deals with capillary filtration and absorption, which happens by a process called bulk flow. And within bulk flow, you have two forces involved. You have hydrostatic pressure, which is the force exerted by the blood against the capillary walls, and you have osmotic pressure, which is the osmotic force exerted by the proteins within the capillary walls, and it's often referred to as the colloid osmotic pressure. So, when capillary hydrostatic pressure exceeds the combined osmotic pressure, fluid filtration occurs, as seen in the left of that picture that I have there. And this allows nutrients and oxygen to be delivered to the tissues, whereas when osmotic pressure predominates, fluid absorption takes place, which prevents excessive fluid loss and it maintains the integrity of the circulatory system. And this is a delicate balance, and it's crucial for tissue health and overall physiological homeostasis.
My name is Catherine Davis, and I'm going to be going over some learning objectives in Chapter 15. So the first thing we're going to cover is myogenic autoregulation. So myogenic means originating in muscle tissue. Autoregulation means self-regulation. So when you put them together, it refers to how vascular smooth muscle regulates how contracted or dilated it is. And this happens because arterioles can respond to pressure. So if you have a lot of blood pressure, it'll stretch the walls of the arteriole, cause the arteriole to constrict, which increases resistance, which decreases blood flow in the vessel, which will then decrease the blood pressure. And then that's the first learning objective. The second learning objective is about paracrine signals. These have to do with local control, and the molecules we focus on are oxygen, carbon dioxide, and nitric oxide. So there's two processes involved with paracrine signals. The first is active hyperemia, which is a normal process. It's when increased blood flow accompanies increased metabolic activity. So when you have a tissue that has an increased amount of aerobic metabolism going on, you're going to have low oxygen and high CO2. And then these two combined, these two factors will dilate the arterioles, which brings more blood into the tissue, replaces the lost oxygen, and removes the waste product. On the other hand, you can have reactive hyperemia. This is also an increase in blood flow, but it's due to a period of blood loss or of low blood flow. So that's why it's reactive, because it's reacting to occlusion. So when blood flow is occluded, you're going to have low levels of oxygen, and CO2 is going to accumulate in the interstitial fluid. And then you need to remove that occlusion. Once it gets removed, you'll be left over with an increase in nitric oxide and carbon dioxide, and this will trigger vasodilation. So you have more blood coming in that will give more oxygen and take away the carbon dioxide from those tissues that weren't receiving enough during that period of low blood flow.